So, we are going to study the Runge-Kutta methods. It's popularly called as a RK method, and this is one of the most popular methods of solving a differential equation. So, this is how it is written. It's Runge and Kutta method, okay, and in short we will call it as a RK method. So, RK methods represent a family of one step methods to solve the initial value problems. Okay. So, this is one important thing, and the other important thing is that this RK methods achieve the accuracy of Taylor series expansion. We have seen that the Taylor series expansion give solutions of these differential equations or these initial value problems. Taylor series methods without requiring to compute higher order derivatives. Okay. So, this is an important step, because computing higher order derivatives in a computer is actually introduces the process introduces a lot of error, and it's if one can avoid it, it's best to avoid it. So, this method also gives you a way to achieve the same accuracy of these Taylor series expansion without we do not have to calculate the higher order derivatives. In fact, it's the first order derivative that is important, and sometimes the second order derivatives are needed. So, how do we calculate the solution of an initial value problem or a differential equation using this RK method? The formula is simple. It's an iterative solution, as we have seen earlier. So, this is equal to yi plus a slope. I will simply write that as a slope. We will see where the slope is calculated, and this is an interval size. Okay. And pretty much this is the formula that we have seen for calculating the solution of these initial value problems via Euler method or via the Hume's method that we have seen. It's accepting that where you calculate the slope is important. Okay. And this slope, let us call this as y I equal plus m h, and this m is the slope calculated at several points between the initial point I and the final point I plus 1. But not only that, this m consists of different weights of the slope taken at different points, and these weights have to be decided based on certain considerations which we are going to see here. Okay. So, m importantly is the weighted average of slopes at various points in the interval yi plus 1 and yi, that is in the interval h. Okay. So, let us see that how this weights are calculated. So, this is in fact one should not write it y, but rather it should be written as x. These are the points at which these are the slopes are calculated. So, this is on the x axis. All right. So, so we write this weighted slope as W1 M1 plus a W2 M2 plus and so on, and a WR MR, assuming that there are R points between xi plus 1 and xi, and each of width h. I mean these the width between, or the distance between the xi plus 1 and xi is h. So, Wi denotes weights of the slopes at various points, and MIs, these MIs are computed as follows. So, M1, that is the first slope, is nothing but the slope at the initial point, which is the function itself. M2, importantly, it uses the slope M1, it is a xi plus A1h and yi plus a B11 M1h. We will specify what this A1 and B11 are, and so on, and this M3 is the value of the function plus a A2h and a yi plus B21 M1h plus a B22 M2h. So, the slope at the slope M2 uses the value of the slope M1, which is the value of the function, and similarly the slope M3 uses the value of M1 and M2 both, and so on. So, there is a you can write it for the R MR, which is the rth slope, which is equal to xi plus a r minus 1 h, and there is a y1 plus a br minus 1 1. If you allow me to put a comma here, because otherwise okay, we can avoid putting that comma by just putting this into the inside a bracket. So, br minus 1 1, which is that 2 1 here, and that is a M1h plus and so on, and then there is a br minus 1 r minus 1 mr minus 1 h and so on. So, it uses all the previous slopes that are computed, and if you wish to write it like this, you can write it in a compact form. Let me write that. So, just once again writing M1. So, this is for r equal to 1, and MR in a compact form MR can be written as f xi plus AR plus 1 h, and then a yi plus h, and there is a sum, and then there is a br minus 1 j mj. J starts from 1 and goes up to r minus 1, and this is the rth slope for r to be greater than equal to 2. So, 2 onwards you can write this. So, note a few points may be noted here, that one is that the computation of slope at any point involves the slopes at all previous points. So, this is the difference between the Euler method or the Hume's method, where you have chosen certain points and have calculated the value of the slope at those discrete points, and they have no relationship with each other. I mean, maybe the you require some data, but they are sort of independent, where here the slopes in this RK method, the slopes are all interlinked, which means that slope at the rth point requires the value of the slopes at all r minus 1 points that are there before. Okay. And the slopes are computed recursively using the above equation, starting with m1, which is equal to nothing but the slope at the initial point. Okay. And third, the RK methods are known by their order. We will soon see what it means. That is, there could be a second order RK method. The first order RK method is by default the Euler method. So, there could be a second order, or there could be a third order, or there could be a fourth order, or even higher orders of RK method. So, this is, for example, RK method of rth order when the slopes at the r points are used to construct the weighted average slope m. Okay. So, this is the thing that we need to know about this computation of this RK method. And so, as I said earlier, that importantly, I mean, RK method of first order is called the Euler method. You need to convince yourself, but it is very easy. So, let me box this. So, we will actually talk about RK methods of second order onwards. Now, talk about determination of the weights, which is the most important thing here. Okay. So, we need to calculate these A1, A2, B11, B12, etc., and hence that those will help us to calculate the M1 and M2 and so on. So, basically we need to calculate the weights at different points, and the number of points you choose that determines the order of the RK method. So, in that interval h, if I choose say a set of 3 points where I would calculate the slope, then it is called as the third order RK method. If we choose that number to be 6, then we will get a sixth order RK method. Okay. So, it depends on the number of points. All right. So, let us talk about just a second order to begin with. We will of course generalize it to higher orders, or at least do third and fourth order. Specifically, let us talk about the second order for ease in derivation. So, second order RK method. All right. So, one has a yi plus 1 equal to a yi plus a w1 m1 plus a w2 M2 and H. Okay. And so that is the two slopes at the 2 points that we have decided to compute. M1 is easy, which is just the given problem itself, that is your y prime, which is nothing but f x I y I, that is at the initial points. Let us call this as 1a, and M2 is f x I plus a1 h, we have written that earlier, y I plus b11 m1 h, and let us call it as 1b. Okay. So, we have to determine the weights. So, how many unknowns are there? You have a W1 unknown and a W2 unknown, A1 unknown and a B11 unknown. Okay. So, these are unknowns. So, the key method, or rather the key point here that the RK method uses is that these parameters, what I mean is that these W1, W2, A1 and B11, these parameters are chosen such that a power series expansion on the right hand side of equation 1, a power series expansion matches with this one, equation 1, the right hand side of equation 1. Let us see what that is. So, agrees with the Taylor series expansion. So, basically what is written here has to match with the Taylor series expansion of y I plus 1 in terms of y I and f of x I y I. Okay. So, this is very important, and this is how the derivation proceeds, or rather the identification of the values of W1, W2, A1 and B11, that will have to proceed by rather comparing or matching this equation 1 to the Taylor series expansion of y I plus 1 in terms of y I and the slope. And we know pretty well what that is. So, this is the second order Taylor series expansion it is like y I plus 1, it is equal to y I plus y I prime h plus a y I double prime by 2 factorial h square. Let us call this as equation number 2. So, this is given y I prime is nothing but f x I y I, and for convenience let us write that simply as f, and now we have y I double prime, which we would write it as df dx. So, this is a function of both x and y. So, we will take a derivative with respect to x, and also there will be a partial derivative with respect to y, and so on. Okay. So, this notation we are very familiar with, and this is the double derivative, which is f x plus f y and the value of the function. So, if we put all these things in 2, so let us write putting in 2. So, yi plus 1 equal to yi plus f of fh plus f of x plus fy f h square by 2. Okay. Let us call that 3. Now, if you compare the right hand side of 3 and the right hand side of 1, let us just take you back to 1. So, that is W1 M1 and W2 M2 into H. So, of course, there is a Y1 there, YI there. So, we have a YI and then all these things. So, this must be that W1 M1 plus W2 M2 and H, because that is an expansion, the power series expansion, and this one is actually the Taylor series expansion taken up to the second order. So, if we actually look at the slope M2, so from equation 1b, M2 becomes M2 is given as, just to remind ourselves, it is a A1H and yi plus B11 B11 M1H and let us just call it as 4. If I expand this M2 about xi yi of this, do a Taylor series expansion, I will get a f xi yi, that is the first term, and then it is a A1H and then there is a del f del x, which is, we write it as fx, plus a B11 M1H fy and plus order h square. Okay. So, I do a Taylor series expansion. About xi yi. Okay. So, that is your M2, and if you substitute that, let us just write this as equation 4, because that was already written there. So, if I substitute equation 4 in 1 and replacing, of course, your M1 equal to f, M1 is nothing but f. So, this is, so putting 4 in 1, we get yi plus 1 equal to yi plus there is a W1 f, remember M1 is nothing but f, a W2 f plus a W2 A1 h f x plus a W2 B11 f, which is M1, and fy h, and we are missing out terms which are of the order of h cube. If I rearrange this a little bit, then this becomes equal to W1 plus W2 f plus sorry, there is a h also, and there is a W2 A1 fx plus a W2 B11 fy into h square, and then of course, we are skipping terms from h cube onwards. So, let us call it as equation 5, and if you compare the right hand sides of 3 and 5, then we can write. So, W1, so you see that FH comes with a weight 1. Okay. So, there is 1 here. So, we will call it, so W1 plus W2, which is the weight of FH term, it's equal to 1. Now, you see that H square comes with a Fx plus Fyf. Okay, Fx plus Fyf divided by 2 is the H square term. So, H square term is this. So, we can see that the Fx, so W2A1, it's equal to half, because there is a factor of 2 there in equation 3. So, this W2A1 is equal to half, and similarly W2B11 is also equal to half, because that is the coefficient of FFy. All these are fine, but then you land up with a problem that you have 4 unknowns, namely A1, A2, sorry, let us write it as the ones that are there before. So, W1, W2 and A1 and B11, okay, and only 3 equations. So, an unambiguous solution is not possible, but then even if we do not get an unambiguous solution, we get a family of solutions, and this is what makes this method very powerful, and one can actually look for different alternatives among the family of solutions in order to get the best solution, or rather the ones that has the minimum error. Okay. So, one choice, first choice, say let's do it on a different page, first choice, and the first choice we can take as W1 equal to half equal to W2 and A1 equal to 1 and B11 equal to 1. Okay. So, W1 and W2 to be half and A1 equal to 1 and B11 equal to 1. See what it gives. So, we get a yi plus 1 equal to yi, and it is a m1 plus m2 divided by h. I am so sorry, m1 by m1 plus m2 divided by 2 into h. If you recall, this is nothing but the Hume's method, where we have taken 2 points at the 2 extremities and taken their weights to be equal to half. Okay. So, we have taken the initial point I and the final point I plus 1, calculated the slopes. The slopes are called as m1 and m2, and while you iterate the solution, the slope that is taken, the effective slope that is taken is m1 plus m2 divided by 2. Okay. Where of course, just to remind you that this is equal to xi yi, and m2 requires the slope requires the slope of m1, I mean this slope evaluated at the point xi yi, and so this is at this point, at the end point, and the slope is needed here. Okay. So, we need to calculate this value and put it back and calculate the slope, etc., and so on. So, this is the slope at the beginning of the interval. And this is the slope at the end of the interval. Okay. And so, we can make a comment that the second order RK method is Hume's method, basically without the iteration. So, if that is the thing, let us look at one more choice. So, let us take W1 equal to 0, W2 equal to 1, A1 equal to half and B11 equal to half. So, then the second order method gives yi plus 1 equal to yi plus a m2h, and the m2 is actually xi plus h over 2 y1 plus m1 by 2 into h. Okay. So, what it says is that it is called as the midpoint method. So, this we directly calculate a slope m2 with m1 being equal to, so of course, m1 is nothing but equal to f x I y I. So, by calculating the slope at the midpoint, we iterate the solution. So, we do not need to calculate it at the two extremities, we can only calculate at the midpoint, but for knowing the midpoint we need the 2 points at the extremities and so on. Let us take a third choice here itself. Okay. This is called as a midpoint method, and this third choice which we are going to do is called as a Ralston's method. So, let us see what that is. So, one can choose a W1 equal to 1/3, a W2 equal to 2/3. So, it is a and which fixes this A1 equal to 1/3 and a B11 equal to 3. So, W2, so W2 being equal to 2/3. So, for this will have to be half, this will have to be a 3/4. Okay. So, B11 equal to 3/4. Okay. And this is known as Ralston's method. Let us see what the solution that I get is yi plus 1 is equal to yi plus a 1/3 m1 plus a 2/3 m2. So, it still is at the at 2 points, but the slopes, the weights have not been taken to be equal, rather they have taken to be in the according to weights 1/3 and 2/3, and so m1 equal to again xi yi and m2 is equal to f xi plus a 3/4 h and a yi plus a 3/4 m1 h and so on. Okay. Now, one can see that whether the first choice or the second choice or the third choice, they give correct results, and comparison necessarily needs to be done in order to understand that which of the rather which member of the family of RK methods, second order RK methods give you the correct solution. So, let us do the comparison of various and let us take this example, so that f x we can write it y also, but this is only a function of x plus 12 x square minus 20 x plus 8.5. So, you integrate this. So, what it means is that your y prime or dy dx equal to this. So, from 0 to say 2 for example, or 4, whatever, we are anyway not going to do that, but we will show it for one step, and then you can repeat the calculation. So, integrate this from x equal to 0 to 4 with a step size of 0.5. H, so this is equal to h, and the initial condition being f of 0 is equal to 1. Okay. So, let us do the midpoint method, or rather this the Hume's method, say for example, and that is equal to, so m1 at the first this thing which is at x equal to 0 is minus 2 into 0 cube plus 12 into 0 square. So, you put 0 because 0 is the initial point and m1 is the slope at the initial point. So, we are giving the answer here 20 into 0 plus a 8.5. So, this is equal to 8.5. So, m1 equal to 8.5. So, m2 which is to be calculated at the midpoint. Okay. This is the midpoint method that we are talking about. So, so this is, let us just write it here. And of course, you can also do Hume, which is easy to do. So, this is the midpoint method, and so m2 is equal to minus 2, and we have to calculate it between 0 and 0.5, that is the interval. So, we will calculate it at 0.25. So, this is 0.25 cube plus a 12, 0.25 square minus a 20, 0.25 plus a 8.5, that is equal to a 4.21875. So, I get the slope. So, if we want to use the Hume's method, then we will take the slope to be m1 plus m2 divided by 2. So, average slope if you want, which of course refers to the Hume's method, which is equal to m1 plus well, I mean in the sense that if we so if you compare the slope itself with Hume's slope, which is nothing but m1 plus m2 by 2, which is equal to f0 plus f of 0.5 by 2. So, instead of 0.25 here, you can put a 0.5 and then take a half of the slope. So, this becomes equal to, if you calculate it, it becomes equal to 4.4375, and the slope of course in the midpoint method is different. So, this is the Hume slope. Okay. And the slope becoming different, the values will start getting different, and of course, the Euler slope to Euler's slope this is nothing but 8.5. Okay. So, the Euler slope is very large, whereas these two slopes, the Hume slope or the midpoint slopes, are somewhat having similar magnitude. All right. So, what we have to do is that we have to suppose we are doing the midpoint method, we have to substitute the slope into the iterating equation. So, the value at 0.5 is 1.421875, and then one can multiply it by 0.5, one would get a 3.109375. Okay. So, we got the value of y, that is the solution at the first, at the end of the first interval as 3.109375. All right. So, now we will take this value at this beginning of the interval. So, that is now the M1 for the next interval. So, M1 would be 3.109375. Now, we will have to calculate M2. M2 is again at the middle point of the next interval, which is between 0.5 to 1. So, we have to take a 0.75 and then calculate this here. All right. If we use both, then we can calculate y at 1 and then continue for the next one and so on. I think I have given you the hint how to calculate using the second order RK method with the midpoint. I have not discussed this Hume's method, but you can also go and do the Hume's method, just that we have to calculate the slopes at the beginning point and at the end point, and then each will have a weight of half. So, it is M1 plus M2 divided by 2. So, now let us come to the Ralston's method. So, M1 is calculated as 8.5. M2 now has to be calculated at the 1/3 point, or rather the 3/4 point. So, if you divide your 0.5 into 4 equal intervals and then you take 3 of that, which is 0.375. So, it is minus, I mean this is 0.375 whole cube plus 12 into 0.375 minus 20 into 0.375. So, this square and so on, and 8.5. So, this becomes equal to 2.582031. So, you have M1 equal to this and M2 equal to this 2.582031. So, the average slope or rather the effective slope, whatever you want to call, this is equal to 1/3 of 8.5 and plus a 2/3 of 2.582031, and this is nothing but a 3.277344. So, you see that we are, the Hume slope is 4.4375, the midpoint slope is 4.21875, and this is 3.277344. So, of course, these values, the slope values differ, and hence the final results will also differ. I will not proceed, but you finish this, at least do it till if you want from x equal to 0 to x equal to 2, and you can take the interval to be 0.5 and then at least do a comparison of these different second order methods for you to be convinced that among the family there would be some methods which are more efficient and will inflict less error in the final calculation of the initial value problem. All right. So, let us do this third order, or rather we can do another problem of course, but maybe we will catch up in the tutorial on these different second order methods. But I hope you have gotten an idea that how to go ahead doing these. These are all like Taylor series expansion but then you do not have to calculate the higher order derivatives, and it is only the first order derivative that is needed. So, coming to the higher order RK methods. So, let us first discuss the third order RK method. So, we can perform a similar derivation as the second order RK method to arrive at results. We will not give you proofs of that, but it can be done. The only problem here, the problem becomes worse in terms of the deficit of the number of equation as compared to the number of unknowns. Previously, we had in the second order method, we had 3 equations and 4 unknowns. Here we have 6 equations and 8 unknowns. Okay. So, all right. So, we state the result without proof here. It is y I plus 1 equal to y I plus 1 over 6 m 1 plus 4 m 2 plus m 3 into h, where m 1 equal to f x I y I, m 2 equal to f x I plus h over 2 y I plus half m 1 h, and m 3 equal to f x I plus h y I minus m 1 h plus 2 m 2 h, and so on. Okay. And similarly, the fourth order RK method, let us do it in a different slide. So, it yields the following set of formula, where your y I plus 1, it requires of course 4 slopes to be computed at 4 discrete points. So, it is a y I plus 1 equal to y I plus m 1 plus there is a 1 over 6, and there is a 2 m 2 plus 2 m 3 plus m 4 and h, okay, where m 1 is f x I y I, m 2 is equal to f x I plus h over 2 y I plus m 1 h over 2, m 3 is equal to f x I plus h over 2 y I plus m 2 h over 2, m 4 equal to f x I plus h y I plus m 3 h, and so on. Okay. So, this is the fourth order RK method, and these the last two we have presented without any proof, but let us do an example for the fourth order RK method. So, the two examples that we are going to do, one for the second order and one for the fourth order. Okay. So, it is a dy dx which is equal to y prime which is equal to y minus x, and the initial condition is given as 2. So, the statement of the problem is that find y at 0.1 and y at 0.2, say correct to 4 decimal places, just to specify more clearly. Places using a second order RK method. Okay. This you have seen, just for the practice I am including this. So, I will do a y1 equal to y 0 plus a half m 1 plus m 2 into h. We have m 1 equal to f 0 and m 2 equal to f x 0 plus h y 0 plus m 1 h. So, take h equal to it is not specified, but we can take anything that we feel correct. So, this is m 1 equal to as a value of the function. So, that is equal to 2 and m 2 equal to f. So, this is x naught plus h. So, this is 0.1. So, 0 plus 0.1 and this is like 2 plus. So, this 2 into 0.1 that is 0.2 and this is equal to 2.1 if you calculate it. So, this is m 2. So, what I get is that y 1 equal to y 0.1 equal to 2, which is y at 0, and then half into 0.41, which is equal to 2.2050, calculating it up to 4 decimal places. Now, we will call this the next interval as a y 2, which is equal to a y at 0.2. So, there of course, the initial things are taken as 0.1, y 0, that is f, which is 2.2050. Now, y 1 becomes equal to y 0 and m 1 becomes equal to 2.105 and m 2 becomes equal to when you calculate it, it becomes equal to 2.4155 minus 0.2 and we can calculate it and put it there. Okay. So, this y 2 becomes equal to, which is y at 0.2, it becomes equal to y at 0.1 plus half and 0.2105 multiplied by h. So, we can multiply it by h and this becomes equal to so this becomes equal to 2.2155. So, this when it gets multiplied with h which is 0.1, it becomes this. Okay. So, this is equal to 2.4210. Okay. All right. So, this is y at 0.2 and so on. This is what is needed. So, y at 0.1 and y at 0.2. Similarly, we can calculate y 3 equal to y at 0.3, that becomes equal to 2.6492 and y 4 equal to y at 0.4 equal to 2.8909. Okay. So, basically we are using this the midpoint method and to calculate these slopes and so on. So, the analytic solution of this is so y equal to x plus 1 plus exponential x. So, the exact value y of 0.1 equal to 0.1 plus 1 plus exponential 0.1, it becomes equal to 2.2052, whereas what we got is not too bad, it is equal to 2.2050, where it is 2052. So, the midpoint method in this particular case, midpoint second order RK method, deviates only in the fourth decimal place. So, similarly of course, the exact value of y point 2 is equal to 2.4200, whereas we got 4210. So, that is in the third decimal place. So, deviation only in the third decimal place. All right. So, let us just look at a fourth order method, and then we can close this discussion on the RK method. So, the its integrate f x y, it is equal to 4 e 0.8 x minus 0.5 y using step size of 0.5, initial value y 0 equal to 2 from x equal to 0 to 0.5. So, to begin with, the slope at the beginning of the interval this is equal to m1 equal to f02, which is 4 e 0.8 into 0 minus 0.5 into 2, which is equal to 3. So, use this value to compute a value of y and slope at the midpoint. So, this slope has to be calculated at the midpoint. So, all right. So, y at the first interval, because you are going from so h is equal to, so the at the middle of the interval it is 2 plus 3 into 0.25, which is equal to 2.75. Okay. So, this is the value at the midpoint. So, that is the slope, and hence your m2 will be f of 0.25 and 2.75. So, this is nothing but 4 e 0.08 into 0.5 minus 0.25 into 2.75, it is equal to 3.5106 11. Okay. Now, we will use this slope to compute another value of y. And another slope at midpoint. All right. So, what we do is that we calculate this y at 0.25, which is 2 plus 3.510611 and multiply it by 0.25. So, that becomes my M 2. So, it is 877653, and hence the M 3 is equal to 0.25 and 2.877653, and this is nothing but equal to 4 e to the power 0.8 into 0.25 minus 0.5 into 2.877653, and that is nothing but if you calculate it, it is equal to 6785. So, we calculated we have calculated this slope M 3. Now, this slope M 3 is used to compute a value of y and a slope at the end of the interval. Okay. So, y at 0.5 is equal to 2 plus 3.446785 multiplied by 0.5, which becomes equal to 3.723392 and so on. So, M 4 it's equal to F 0.5 3.723392, which is equal to 0.8 0.5 minus 0.5 3.2 sorry 72 723392. All right. So, if you calculate that, that becomes equal to a 4.105603. So, I have calculated 4 slopes at 4 discrete points, and these are going to be used to update the solution at the end of the interval. So, the M, the effective M or the net M is 1/6 3 plus 2 into 3.510611 plus 2 into 3.446785 plus 4.105603 and so on, and then if you calculate the slope, it becomes 3.503399. So, using the fourth order method, I get the solution at the end of this interval as 2.2 plus, that is y 1, that is y at 0, basically at x equal to 0, which is value 2 that is given, 3.503399 multiplied by 0.5, and this becomes equal to 3.751699 and so on. Okay. So, by and large, I have given you an idea that how these initial value problems are solved. We have first discussed Euler method, which is calculating the slope and updating the solution by the slope computed at the initial point. The Hume's method was one better than that, in which the slope at both the initial and the final points were calculated, and the average of the two were taken, in the sense that average means just multiplying each of the slopes by a factor of half, and then that is considered as the effective slope. In the RK method, we saw that we can actually divide in the interval h, we can take several points, and in those several points there is no reason for us to take an a priori weight. We can take these weights to be some values which satisfy certain equations, and then we can build up actually a family of methods, higher order, second order and higher order methods. And second order is easier to handle for us. So, we have seen three kinds of methods. One is of course the midpoint method, the other is the Hume's method, which already we have learned, and then the Ralston's method. And then it turns out that amongst these we have a very large family of methods. It is not, the list is not exhaustive. And then we have looked at at least the formula, working formula for the third order Runge method and the fourth order Runge method. And here we do an example of the fourth order Runge method, in which the slopes at 4 different points had to be computed, which are pretty easy to do, and then these slopes have been used in order to update the solution at the end of the interval. Okay. And then you have to take all these input for the next interval and then again update the solution, in the sense that this value of y at 0.5 will be actually taken if you have the range to be say from x equal to say 0 to 2, not 0.5 as we have said here. If you have that range, then you can actually update the solution, taking this as the initial solution and then all calculating again M1, M2, M3, M4, and then put these weights such as it's shown here, and then update the solution to get a y at 1 and so on. Okay. These Runge methods are very popular numerically. A lot of work actually use these methods, some either second order or fourth order methods in order to calculate the solution. We will see some practical applications in the next discussion.